So let's formalize chapter 1 in 2 videos. So if you look at the table of content, we actually only need section 1.2. And once we formalize that, we're going to use the reading questions to see if we've really done a good job in formalizing everything in the chapter. In this video, we're going to only talk about set, and the next one we'll talk about function, relation, and everything related to that. So let's begin on set. So the best way to start formalizing a section is to first mark down the things in that section that could be formalized. So there's some nuances about which one should be formalized. So let's walk through this section. So first we have a set. The first concept is very apparent. So the good thing about this textbook is that I have every concept bolded. So we're going to mark this down. Here, the element or member is also bolded, but we're not going to formalize it because it is not a separate mathematical concept. It's kind of a membership belonging to this set, so we are not going to do that. You can see the examples here. You can just easily ignore them because they are not going to be helpful for formalization. And then we hit our second concept, which is a bit ambiguous, because here it says a set A is a subset of B, satisfying this notation. So is subset really a thing? Is it a mathematical construct, or it is a relational kind of a decorator on a subject? So for example, when you try to define a set B, and you want it to be a subset of A, so would you always think about B as a set or as a subset to A? So the resolution is this. Whenever we have an object, we always think about what this object is. And is it necessarily produced by other object? So without A, is B still exist? The answer is yes, because subset is not a constructor. It's not a unique way of producing B from A. We can produce various subsets from A, but there's no unique way to produce B from A. So if you model B as a subset, taking A as a generic, that will just be super weird because you don't have the implementation to produce B precisely from any A. So that is why we're going to model subset as a predicate. So internally, a predicate is modeled by relation, which basically is a constructor for proposition. So here you take in some set and you're going to produce a proposition that can be proven or true. And you're going to produce some proposition either assumed as a hypothesis or treated as a theorem for us to prove. And following the subset is a proper subset. And we can definitely model proper subset as a separate predicate from subset. And again, proper subset is not a new kind of mathematical object. It is a relation concerning two sets. So we're still going to model this as a relation. And the thing you're going to notice is that proper subset actually built on top of subset. So it shares some of the information from subset. So in order to be information efficient, we're going to combine them into one relation block. And the way to do this internally is to use a prop modifier return type for the relation block, which allows you to define different versions of a relation. So by default, it's just the subset. Another variant is going to be built on top of the default. So here we have a variant called proper, and it actually uses the default one and adds additional conditions. So that's really handy. After that, we have equal. So equality is really confusing in pure mathematics because it's actually polymorphic. So for things to be equal in pure mathematics, you have exact equal, you have for example, here subset equal, and then you have frontier mathematics equalities of equivalences of equalities. So you have n order of equivalences in category theory. So that's really not easy to be defined, and that's why we don't support a native equal syntax internally, because things can vary, but you can still render them as the equality using the notation syntax. Here you can see set equal, two sets are equal if they are subset of each other. So A subset of B and B is subset of A. That means A equal to B. And then it's really the one we should use. Next, we have empty set. And this is actually the second object that we see. The first is set. All of this above is a relation. And internally, whenever you have two structures that looks really similar, you should think about their relation. So whether one extends from another or whether they're just completely different thing. So an empty set is clearly a set. So that is why we can try to use the inheritance rule internally to try to connect them together. And so you should think of, should an empty set inherit from set, or should set inherit from empty set? And the answer is because empty set is more specific than a set, it's a special kind of set, so it should inherit from a set. So the parent is always more general than the children. And the way we differentiate empty set from set internally is by adding laws. Because empty set and set have nothing inside, so the only way we can differentiate between them is not by adding different fields. It does not have a special membership function. The only thing empty set have that is more specific than its parent is the fact that it has no element in it. You have to add a law in empty set stating that it will never have an element in it. This is always true for empty set. And because it has no generic, it means it can never be instantiated to a more specific version because the structure itself is in its most specific form. You cannot instantiate any instance out of it. So whenever we use empty set, we're just going to use the structure's name empty set. We don't want it to produce a specific version of empty set. Okay, so that makes empty set unique. What we want to see here is that we have another sentence here saying that the empty set is a subset of every set. Here is another ambiguity. So should we model this sentence? Because this is a really handy one. So imagine you have a proposition where S is a subset of A. So if you can manage to prove S is an empty set, then this theorem will be proven. So here you can either model it as an axiom or a proven theorem. So either way, you will be allowed to use this proposition in your proof. But here we're going to model it as a theorem just for practice. So next concept is the union. So here we have another problem because it actually provides a way to construct the object in the final form. Should we model as a relation? I don't think so because it ultimately creates a set with a deterministic way of constructing it. It's basically combining elements from A and B inside. And there is a unique way of doing this. So that's why we may choose to model it as a structure. And if you look at the generic of the structure, it actually passes A and B. So when we instantiate a union of two sets, we can just pass in the two sets that are involved by the union. And to characterize any union, we're going to use this axiom, which looks exactly like the textbooks. So here is what I mean by symbolic modeling. And we are only using proposition to define what the structures is behaving. So that is handy. Only in this way, we will have the symbolic power to progress a proof when it involves a union. So the same thing with intersection. It takes A and B, and it has this defining law. And wait a minute, what is union and intersection? They're actually a set. And just by looking at the structures, you have no way to tell that it's a set. So what we're going to do is let them inherit from set. So in this way, no matter how many laws you have, how specific rule you want to make, they're still a set. And I know that this structure looks really like a function that it takes in some set and try to produce something, but it is still an object. But with the formal proposition as the constraint to guarantee they will produce the right result, even though we don't apply it as a function, even though we don't apply it. So when these structures are used in the theorem, they are guaranteed to progress in the right direction because we have the proposition. And this is what computational modeling cannot do. Next, we have disjoint. I will give you one moment to think about it. Now, it says when two sets has no element in common, they are said to be disjoint. So these two sets, there's no order. So you cannot model one set as a generic of another set to make this disjoint as an object. So that is why disjoint must be modeled by a relation because it takes two things. And it does not produce another set. So that's why it's a relation. And the defining proposition of this relation is that there is no intersection between A and B. So, which, in other words, A intersect with B is the empty set, okay, which makes sense intuitively. Next is the definition of universal set. So precisely, universal set is used to help the definition of complement. Again, a complement of A looks like a set, so it must be modeled by a structure because it's a thing. And the way to construct it is that we need to define the universal set, and then we're going to have a law such that, so the complement of A is a set where everything is in the universal set, but not in A. And A's element is all in the universal set. And so this will be modeled by a structure inheriting from set and have this one rule. So here we just assume U is a bigger set than A, and that's it. So next we have the difference of two sets. And here just feels like a union or intersect type of set. So it's still a set modeled by a structure. And the rule is that for every x in A, it's not in B. But here is another surprise here, because we actually have two equalities. And the first equality says that difference of A and B is actually equal to the intersection of A with the complement of B. This is clearly a different theorem. We can actually prove it right here. But for simplicity, you might just want to attach it as a law because the textbook does it. But it's better to model it as a theorem for your own understanding. But it makes no difference when you try to apply it in the proof. Voila, we just finished collecting the definition for set. And modeling all of them internally is really straightforward. We have all of the definition about set. Now the textbook introduces some proposition for us to prove. And here there's another theorem for us to prove. There are three big propositions. But here we actually have a theorem that contains 6 parts. And wait, actually in each part there's another 3 parts. But in each subproposition we have another layer of proposition. The first proposition have 3 subpropositions. The second and third and fourth have 2 subpropositions, and fifth and sixth have only 1. And the nice thing about Ternland is that it allows you to combine all these propositions in a block style, so that you can attach a proof block to an individual leaf node in this proposition tree. So let's see how this theorem are actually proven in Ternlang and compare it with the textbook to see what's actually missing in the textbook. So let's look at this proof carefully. So firstly, we expand what set equal means. Notice that it is rendered as a equal sign, but it's actually using the definition of set equal, wrapping the left-hand side and right-hand side. And next, we unfold the concept of subset, which is another definition, and just expand it into 2 implications. So then we're going to look at these 2 cases simultaneously. So we're going to split it into 2 parts and prove them separately. So once these 2 branches are proven, then this goal will be proven. So you just go to this first branch where we have this implication. So in formal logic, to prove an implication, the premise of the implication is actually part of the assumption. So we use another tactic to simplify this goal. Now we have the in operator. I forget to mention that in operator is only available if you make a structure, a container like this, using the square brackets. So the in operator is the most basic operator in Ternlang. It's a native operator that does not have any definition to be unfolded. So now we're just trying to find something in the context or another theorem that can match this, that can try to prove X in A. So if you look at H, we can actually break it down again because there's another union symbol. So that's how we do it. We unfold the union into another implication. And we break it down into the OR operator, remember? So here it really looks like textbooks where we have 2 operators of X in A and X in A, and then we're trying to prove X in A. So here we have a logical OR, and we try to reduce them. So here it seems like we can just close this branch by collapsing X in A or X in A into X in A. But actually we cannot do that unless we have some smart tactics that match X in A with both branches. So in formal logic, if you have a assumption that is a disjunction and logical OR, you have to break it down again. So you have to prove it either way that the statement is true. So that is why we try to break this thing again by breaking the assumption H into 2 parts. One is H with the right-hand side and H with the left-hand side. So after breaking it up, we now have 2 goals whose assumption matches exactly the proof statement. This is how we can mark a proposition as true. So after we're closing the split, we're closing this branch, and then we move back to the original, to the first branch, and then go to the second master branch, which is a reverse way from the previous. So the first branch is proving X in union A and A implies X in A. And now we're proving X in union A and A, assuming X in A. So this is a little bit different. And so what we're going to do is, again, move the premise to the context and then unfold the union, which now gives us an OR operator in the goal. And this is really different. So instead of branching, they could just reduce the goal because because either one is true. So we just prove one of them, and immediately we have the same assumption versus goal. So now we can prove this branch as well. So now we have just proven 2 branches of the goal, and the whole proof is finished. So I know what you're thinking. This is really complicated, isn't it? Textbook only has 3 steps, but I have 12 steps. So why are we doing this? And the reason is that this is a really small proof, but for a bigger proof that relies heavily on a rigorous, exhaustive and a case analysis on all of the possibilities, this becomes really handy. And the textbooks really struggles to do that. And we can see it immediately in the next theorem, the De Morgan's law. Proof for this simple equation is actually quite long, and natural languages struggles to do a very clean separation of each case, and it is very unclear how each branches end and how each branches create new branches. And for some case analysis, it's even very descriptive and even jumps ahead. And it makes a conclusion out of the blue right here. So just by skimming this first chapter, I know that this chapter is trying to prove that this is a subset of this. And I can see that X is in the left-hand side, and I can see X is in the right-hand side, but I see no reason of why the left-hand side is a subset of the right-hand side. And this is really problematic. So this just feels confusing, and there will be lots of these sentences throughout your education. And that is why we need formal method. And that is why we need to do it in a rigorous way. So what Turling does this is actually to start with the assumption we try to prove and try to break it down to verify whether it is true. So it's much easier than thinking about magical steps that can brainstorming conditions that try to assemble to the goal, which is impossible for a beginner to do. It's much better to break the proposition down and try to verify every single piece of them. Learn a subject without any help, without expert insight and the privilege of a good mathematical education. Everyone can do this. So if you have struggled with mathematics, this is not your fault. It's the way that the material is presented. So the proofs of most of this proposition are in the published link in the description below, so you can play with all this proof yourself. So I hope you'll get a more enjoyable experience with learning pure mathematics, and we'll see you in the next video when we'll talk about functions.